This video on proportionality theorems is designed to introduce you to the theorems and how they can be used to solve problems. Let's go ahead and take a look at the first of three theorems that we're going to take a look at today. It says if you have a line that's parallel to one side of a triangle and that line intersects the other two sides, then it will divide them in such a way that the other two sides are proportional. Alright, now like with anything else in math, when we try to put it in words, it ends up a lot more confusing than it necessarily needs to be. So let's go ahead and take a look at what this says in a picture format. What this is saying is it's saying if you have this red line segment TU up the middle of this triangle, and that runs in such a way that it's parallel to side QS, then what it's going to do is it's going to divide the two sides of the triangle proportionally. In other words, if we take a look at this relationship here between TR and QT, that's going to be exactly the same as the relationship between RU and SU. So that's one possible way we could go ahead and write this proportion. Looking at the relationship between RT and QT is the same as if we compare the relationship between RU and US. Now that said, that's one possible way to write that proportion. We could also look at it as top over bottom equals top over bottom, or RT is compared to RU is the same as when we compare QT to US. Notice that both of these proportions are two different ways of writing the exact same thing. In both proportions, when we cross multiply, we're going to be multiplying RT times US and QT times RU. So both of those are exactly the same. And that's important to know because you may have one of them written down on your paper and your friend may have the other one written down, and even though they'll look different, you're in fact both of you are correct. Alright, now the converse of this theorem is also true. If the two sides of the triangle are divided in such a way that they're in proportion, then it must be true that that line is parallel to the third side of the triangle. So again, looking at that in pictures, here's what this is saying. It's saying that if that relationship between RT and QT is the same as the relationship between RU and US, then it must be that the lines are parallel to each other. Alright, so let's go ahead and take a look at and see how this can be used in some problem solving. So in this diagram, they're giving us or telling us that these two line segments are parallel, AB and ED. So the first thing I'm going to do is go mark those two parallel in my picture. I'm going to label the side lengths that are given to me. So side length BD is 8, and I guess that's really not a side, it's just a segment. DC is 4, AE is 12, and it wants me to find the length of EC. So I'm going to call the length of EC X. Well, because these two line segments are parallel to each other, I know that it has to divide these line segments up in such a way that they're in proportion. In other words, if I compare that 4 to the 8, that's going to be the same as what I get when I compare X to 12. So I'm going to go ahead and write that proportion that makes those comparisons. So 4 is to 8, the same as X is to 12. And I can see pretty clearly from this first ratio, the numerator is half the denominator. I'm going to need a value of X that's half of 12. So without even cross multiplying there, I can see very simply that X is equal to 6. Unfortunately though, if I go back and reread the question, they're not asking me to find the length of X, they're asking me to find the length of EC. So I better go back and make very sure that it's spelled out very clearly that my answer here is 6 for EC. Alright, the next one is very similar, except they've given us the lengths of all 4 segments in that triangle. So I'm going to go ahead and label those in my picture first. So L to M is 56, M to G is 21, L to N it looks like is 48, and N to H is 16. It wants me now to make the determination as to whether or not that line segment ML is parallel to line segment GH. Well, I know that these guys can only be parallel if the relationship between these sides are exactly the same. Or in other words, if I go ahead and compare the length of LM with the length of MG, if that comparison is the same as LN and NH. So let's go ahead and make those comparisons and see what we find out. So if I compare 56 to 21, is that the same as if I compare 48 to 16? One simple way that you may or may not remember to tell whether fractions are equivalent or not is just to go ahead and cross multiply. And if their products going crosswise are the same, then we'll know they're equivalent. In this case, the cross products are not the same, and therefore the fractions are not equivalent. And since those sides are not in proportion, those line segments would not be able to be parallel. All right, so that's the first big key idea for today. Next big key idea has to do with angles. It says anytime we have a ray that bisects an angle of a triangle, it will divide the opposite side of that triangle into two segments whose lengths are in proportion with the lengths of the other two sides of a triangle. Let's go ahead and take a look at what this means. What this is saying is that anytime we have this ray CD that bisects angle ACB, so in other words, it chops it into two equal pieces there, then if we're to go ahead and compare the sides opposite those angles, so if we're to make a comparison between AD and DB, that's going to be exactly the same as if we were to compare line segment AC to line segment CB. So this is what our proportion would say. The comparison between AD and DB is exactly the same as what we get when we compare side AC to side CB. Keep in mind, though, there's a couple different ways that we could have written this proportion. We could have said that the comparison between AD and AC is the same as the comparison between DB and CB. Those are exactly the same proportion. Each of them has AD times CB as a cross product, and each of them has DB times AC as a cross product. So two different ways of saying the exact same thing. Let's go ahead and take a look at how this would look in an example. So it gives us this problem where it tells us that the angle's being bisected. So I'm going to go ahead and indicate that in my picture. And the angle that's being bisected is angle BAD. Now it says angle BAD is congruent to angle CAD. So there's BAD, there's CAD. Those are the two that I want to mark congruent. So this one's a little tricky in that they didn't come right out and spell it out that there's a bisector there. You have to be able to infer that by looking at the two congruent angles. Now I'm going to go ahead and mark my side measurements in the picture. AB is 9, AC is 15, D to B is 14 minus X, and D to C is worth X. So because of that angle bisector, I know that if I compare the relationship between side BD and side DC, that's the same as the relationship between AB and AC. So in other words, if I fill in the spots in that proportion, 14 minus X over X is equal to 9 over 15. Now at this point, I'm tempted to go ahead and cross multiply right away. But if I take a minute and look at that ratio, 9 to 15, that's not in simplest form. And I think if I take a minute and put it in simplest form prior to cross multiplying, it's going to make my numbers a little bit smaller and a little bit easier to work with. So in looking at both of the numbers in that ratio on the right there, 9 and 15, I notice that both of them are divisible by 3. So I'm going to go ahead and divide them both by 3. So now I'm multiplying 5 times 14 minus X going in one direction, and 3 times X in the other. 5 times 14, I think I know what that is, but I'm going to go ahead and get my calculator out just to make sure. So 5 times 14 is 70. I'm going to mentally add 5x's to both sides. So now 8x's are equal to 70. Grab my calculator. Hx now is equal to 8 3/4. Or if you like decimals better, 8.75. And since in the question we were asked to find the value of x, I can go ahead and conclude that we are indeed finished. All right, so there's your second of 3 big ideas for the day. That has to do with an angle bisector. The third and last one has to do with parallel lines again. It says anytime you have 3 parallel lines that intersect 2 transversals, they divide those transversals proportionally to each other. So here's what this is saying if we go ahead and take a look at a picture here. It's saying if you have these 3 parallel lines, line R, line S, and line T, and they're intersected by these 2 transversals, M and N, it's going to divide them in such a way that if we were to compare U to W with W to Y, it would be the same as when we compare V to X to X to Z. So if we want to take a look at what those proportions say here, UW to WY, that's the same as the comparison between VX and XZ. And of course there's another way that we could write that proportion if we wanted to. All right, let's go take a look now at one last example. It's asking us to solve for x, and even though they don't come out and specifically state that these 3 lines are parallel, they're marked as such at the diagram. So we know if those lines are parallel to each other, then it must divide those segments proportionally. So in other words, if we compare 4 to x, that's going to be the same as if we were to compare 8 to 12. So I'm going to go ahead and cross multiply. 8 times x is equal to 48. The value of x then must be 6. So those are the 3 big key ideas for today. If you have any questions, please jot them down on your paper now so that you'll remember to bring them with you when you come back to class, or you can always email me. When the next time you come back to class, come back to prepared to practice some of these proportionality theorems.